All right, today we're going to move on to a new topic regarding convergence in law. So in the previous lectures, we have talked about the 4 modes of convergence. So today we're going to talk about the first mode, which is the most, and also the widely used one, and the most relevant to what we call asymptotic distribution. So we will focus on convergence in law. So if you recall, how we write this is actually, let this focus. Is actually xn converges in law to x. That's how we write it. And by definition, if you recall, it's defined as the convergence of the CDF. It's fx xnx converges to fxx for all x in the continuity set. I'm going to write this. So this is a notation we're going to use. So this set C means that it's the point where this function is continuous at. So we write C of a function G. This is the set of points where function G is continuous at. And we call this as the continuity set of G. So essentially, convergence in law requires that for all the values where the CDF of the limit fx is continuous at, we need to have this pointwise convergence from this CDF of the xn to the CDF of x. Okay, so today we're going to give you a very, very important theorem called Halibre Theorem. And this is actually the theoretical foundation of the most important result of convergence in law, the Levy's continuity theorem. So let's talk about Halibre theorem as the foundation. So I would say this is the foundation. And later you will see why. So what Hallibre says is basically a very strong statement. That is, the following 4 statements are equivalent. So the 4 statements are equivalent, which means that you can go from one to the other in any order. And here, the way we write it out is for actually technical convenience, and I'll explain why. So the first statement is we have xn converges in law to x. The second statement is that we have the expectation of gxn converges to expectation of g of x for all continuous functions G that vanishes outside a compact set. And I'll explain this statement later. So for now, let's just say, okay, this convergence holds for any G that satisfies this requirement, that it must vanish outside a compact set. And so now I have a question for you to think about. So here, when we write expectation converges to expectation, we don't need to specify the mode anymore. We don't need to say whether this is convergence in law, in probability, in the Rth mean, or almost surely. Why is that? Why we don't need to say that anymore?
Because it's a sequence of numbers, not random variables.
Exactly, yeah. Once you take expectation, it becomes a number. It's no longer random. Yeah, that's the answer. Yeah, so that's why I think the most important thing for now, if you want to review the materials we have covered is to think about the difference between random variable and the number. That's the whole concept throughout this class. And understanding the randomness, I would say, is the most crucial thing of statistics, and also probability for sure. Okay, this is the second statement. And the third statement actually says, expectation of gxn converges to expectation of g of x. The same statement, but we are making the requirement for g less stringent. For all continuous and bounded function g. So you see, now we just require to be continuous and bounded. We are not requiring the g to have a compact support. Okay, I'll explain B later, but let's go through all the statements first. And the last one is still about expectation of gxn converges to expectation of gx. The same convergence, but again, we make the requirement for g even less stringent. So here we just require g to be all bounded and measurable. Okay, so be measurable is an even less stringent requirement than continuous. We know that continuous functions are measurable. And here we just add one more thing, is that such that the probability of our limit x in the continuity set of G is 1. Okay, so you see the difference. Here, the difference between C and D is that C requires the function to be continuous anywhere, but D doesn't require that. The function G can have some discontinuity point, but I just want to have my limit in the continuity set of G with probability 1. You see, so that's actually so that makes G even more general. Okay, so let's revisit the technical details of B and C and D. What does vanishes outside of a compact set mean? Okay, so compact set is actually a definition in analysis. Basically, what this says is that whenever you have a sequence that converges, and then the limit must be in the same set, and then the set is called compact. So compactness, if you first search for it, compactness is regarding convergence. So what it actually means, I'm going to say it again, is that any sequence in the set that converges must have their limits in the same set. So if the set satisfies that, we call it a compact set. So intuitively, in the Euclidean space, a compact set is a closed set. So that's the easy way to interpret. So everything becomes easier in Euclidean space. So in Euclidean space, Euclidean RD, so, oh, sorry, I'm going to screw this up. In Euclidean RD, the compact set is equal to closed and bounded set. So you can interpret it as like a closed ball, a closed box, a closed cubic. So those kind of things can all be can all inform what you mean by compact set. So specifically in R1, right, one-dimensional Euclidean space, a compact set is just a closed interval. That's the compact set. So therefore, if we just think about everything in terms of one-dimensional, that is, xm is a one-dimensional random variable, the limit is a one-dimensional variable, it's easier to think about it, okay? So if you think about d equals 1, that's the easy case, then G vanishes outside a compact set. It's basically a function that's like this. So you see, this is a compact set, a closed interval. And also G is continuous. Let's not forget about that. So continuous is here and here, right? So we have the continuity in both B and C. And if you have learned this from calculus before, or probably sometimes you didn't learn this from like a easy calculus because you need a little more advanced one to really know this. But what it says is that on this closed set, let's just call it closed interval, but compact set in general, if the function is continuous, then the function must be bounded, must have bounded value. So you can imagine that. So vanishes means, okay, the function is 0 here, is 0 here, right? And so because it's continuous, it cannot have jump. It must go continuously, right? So it can go this and this, but no matter you see how high it goes, you have a bound, you have an upper bound. It cannot be infinity. If it reaches infinity, the continuity will be broken. So that's why you see the continuous function that vanishes outside the compact set and continuous. This will give the result that G is bounded. It cannot go to infinity. That's statement B. Okay, and you see now statement C. Let's say B. Now let's look at statement C. Statement C is a little more general. It doesn't say, okay, the non-zero values of G must be in the compact set. It doesn't say that. So basically, we often call this as the support. So another way to say this is that G is continuous and has a compact support. So when we say has a compact support, it's equivalent to say it vanishes outside of compact set. So these two statements are equivalent. But in C, we no longer require G to have a compact support. The support can be the whole space, can be the real line, but we require it to be continuous and bounded. So which means that the minimum absolute value of G taken over all the values, all the points in the space must be finite. That's the requirement for C. So for C, the support can be non-compact, but G must be bounded. And of course, continuous. So an example of this, if you can think about it, a bounded a bounded continuous function, but that's not having a compact support, you can think about the sine function and the cosine function. Those actually satisfy that. Okay, that's C. And for D, okay, what is measurable function? So the definition of measurable function depends on the measurable set. So we need to first have a measurable set, then we can define a measurable function. So here I'm not going to elaborate on that because that's a measure theory topic. But intuitively, you can just think about measurable function as a bigger function class than continuous function. Okay, so measurable is a more loose concept than continuous. So continuous must be measurable, but measurable may not be continuous. That's the case. So essentially, measurable function, let me just briefly introduce it. A measurable function f, or let's say g, satisfy that for any measurable set B. Okay, for any measurable set B, we have we have G inverse measurable, which we call the pre-image of the set, is measurable. Okay, so that's the mathematical definition of what's a measurable set, measurable function. But here, what we are going to use it is just to broaden C, right? We want to expand C from continuous bounded functions to measurable functions. So what this says that G only need to be bounded and measurable. But still, we want our limit, the sequence limit x, to be in the continuity set of G. So that's why we can worry less about the discontinuity points, because the random variable we care about, the limit, is only in the continuity points. Okay. So this is very, very important. You know, in probability, when we say something happens with probability 1, you see, when we write this, essentially, we are just where we think that, okay, since we only care about x, the limit, this means that x is in the continuity set of G with probability 1. What this implies is that we just care about the continuity points of G. So that's why no matter G is continuous or not, I don't care, because it's not related to my random variable x. So this is just a mathematical concept that makes the condition more general. So the G is not restricted to bounded and continuous. But coming back to the Helly-Bray theorem, I think the most important result, if you just want to know 2 as opposed to 4, is actually A and C. So A and C are the most 2 important statements. A, for sure, it's our conclusion, right? Convergence and law. And C is most interpretable. For all bounded and continuous functions, the sine function is an example. And B and D are more like technical stuff. So basically, the reason we have B here is that when we want to show the equivalence, it's actually easier to prove A goes to B. And then we prove B goes to C. And then we C goes to D, and D come back to A. So basically, it's B and D are mostly for technical reasons, so that the proof can easily go through. Okay, so what I mean is that, so how we can show the equivalence of the 4 statements. So the logic, the proof idea is we need to show A goes to B, B goes to C, C goes to D, and then D goes back to A. And the reason why we can just do this and we'll be done is because we actually have C goes to B very naturally. That's not even need to be proved, right? Because B is a special case of C, and C is a special case of D. So C goes to B, D goes to B. So that's trivial. But here, if we can fill in this loop, right? So you see that we can go from any statement to any other statement. So as long as we can show this whole, prove this whole loop, we already proved the equivalence of all the 4 statements. So that's the idea. Okay, so actually, if we want to go detail into this proof, that will take quite long. So I'm not going to do that for this class this time, but I will give you the ideas behind how we can go from each direction, from each statement to another statement. So at least you will have some intuition about how things work. But before we do that, let's still first give you some interesting examples about why we need boundedness and continuity in statement C. Because I will give you some examples to see that if we don't have that, then it doesn't hold. Okay, so let's first look at some counter examples to show the necessity of boundedness and continuity. So let's think about just between A and C, okay? Like I said, the two most important statements. So why boundedness? What if my G is not bounded? What would happen? So here, let's give you an example. This is a counter example. Let's let G be the identity function. That is, Gx is x, okay? And let's look at the sequence of random variables. Let xn be a discrete random variable. It takes values n with probability n over 1 over n. It takes 0 with probability n minus 1 over n. That's our sequence, okay? Then let's see whether it converges in law. Actually, this is something we talked before, right? So if we think about its CDF, what's the CDF like? The CDF is like we have two discontinuity points, one at 0, one at n, right? So we start from 0, 0, and then upon we reach 0, the probability jumps up to n minus 1 over n. And then it stays as that number, and once it reaches n, it jumps up to 1. That's the CDF. So there are two discontinuity points. But you know, as the n goes to infinity, it will gradually become just one change point, one jump at 0, and this probability is going to 1. This probability is going down to 0. So you can actually see that, okay, by our definition of convergence in law, xn does converge in law to x that is 0. It's convergent to a constant 0. That's the convergence in law. But let's look at the expectation of gx. So here, if we look at expectation of gxn, what's that? A simple calculation will give us that it's equal to 1. And this is not converging to expectation of g of 0 because that's 0. So you see here, even though the g function is continuous, right? Identity function is continuous for sure, but it's not bounded. It can go up to infinity as x go to infinity. So this is a clear violation of the boundedness. And you see here we don't have it. Another thing you can think about is the definition of the convergence in law is actually implying convergence of expectation in a special case. So think about what does this mean? Revisit definition, the definition of this. So today at the beginning of the lecture, we talk about the definition. We said it's regarding the CDF, right? But the CDF itself is an expectation because it's a probability. Okay, so you see that f x n x, what is this? In our first lecture, we give you the definition of CDF, right? It's actually probability of xn less or equal than x. And we told you that this probability can be written as the expectation of an indicator function. So this is actually equal to expectation of indicator function xn less or equal than x, right? And then we can say what? So we can actually write this as expectation of gxn if g y is defined as indicator function y less or equal than x. You see, so if I define the function g in this way, then my CDF is just expectation of GXN. And here you see in the definition, the argument is Y. X is considered as fixed. So what does this GY look like if I define it this way? Think about it. It's a discontinuous function. Okay, let me call this Y. And this is GY. And X is right here. Then what does GY look like? Whenever Y is on the left side of X, I get 1. After that, I get 0. So you see, the function looks like here 1, right? And then suddenly go down to 0. That's my GY. So that's the indicator function. And you see, what kind of G is this? It's bounded for sure, right? It's bounded and it vanishes outside a it's bounded. It doesn't have a compact support because the support is from -infinity to X. This is not compact support. Let me write it down. So this G is bounded, right? This is okay. Compact support. No. And what else? Continuous? No. Okay. So it doesn't have those, but it's bounded. So now you see, the reason we want to use those general statements to prove statement A, which is this, is because ultimately we want to say, okay, this special case of G is a special case of D. So that's why we can go from D to A. As long as we can say, okay, this is a special case of the G function in statement D, that is bounded and measurable. And that X is in this continuity set with probability 1. As long as we have that, then we can show, okay, we have statement A. Okay, but I think it's good to see the connection between the convergence in CDF to the convergence of E expectation G of Xn, because the CDF is a special case of expectation of GXn. Okay, this is like a digression. And let's come back to why we need the boundedness and continuity. So we already give you a counterexample when boundedness is violated and it doesn't hold. Now let's think about why continuity. Okay, we will give you another counterexample. When the continuity doesn't hold, then we have some issue. Okay, so here, let's let G of X to be a discontinuous function. So we define it as 1 if X is greater than 0, 0 if X is equal to 0. So you see, here the definition is continuous because we have a jump at 0, right? It's discontinuous. And we let Xn be a number rather than a random variable. We just let Xn to be 1 over n. Here is a simple case. Random variable reduced or degenerates to a real number. So then you can see as this number, n goes to infinity, this number goes to 0. So we have Xn converges in law to 0. My limit is also a constant. However, let's see what this expectation of GXN. You see, for any of my Xn, it's not 0, it's positive. And it's positive gxn is 1. So you see gxn stay as 1, so is its expectation. And it does not converge to g of 0 because that's 0. And you see, we don't have that. And why is this? The reason here is because we are not actually under condition D also. In statement D, statement D requires allows G to be discontinuous, but don't forget the most important requirement. The limit must be a continuity point of the G. And here it's not. So you see why violation? Why D doesn't hold? The reason is because, you see, here the probability of the limit 0 in the continuity set of G is what? It's 0. This thing doesn't happen. Why is that? The continuity set of G here is actually any value that is positive. This is the continuity set of G. So you see 0 doesn't belong to this continuity set. And because here the limit is a point mass at 0. So 0 doesn't belong to this set means that this thing happens with 0 probability. It's not 1, it's 0. So that's why the statement D doesn't hold. And that's why this is a counterexample. So you see the importance of having the limit in the continuity set of G, even though G might be discontinuous. Okay, so we have seen the two counterexamples to justify the importance of G being bounded and being largely continuous. At least G must be continuous for X to be in the continuity set with probability 1. Okay, that's just the understanding of the Halibre theorem. And now let's look at the proof. So I'll just give you the ideas, the key messages behind the proof. So regarding the sketch of proof. So like I said, we want to prove that circle, right? A goes to B, B goes to C, C goes to D, D goes back to A. So the first thing we want to visit is actually D go to A. That's actually easier, the easy part. So how do we go from the last statement about the bounded and measurable function to the CDF convergence? Okay, so in the notes, we actually talk about the random vector case. That is, xn can be d-dimensional, but here, just for simplicity, I'm going to stick with one-dimensional case. Xn is a random variable. Okay, so what do? We want to show this. So I already gave you the background. That is, we want to show for G, y defined as indicator y less or equal than x, right? We want to show that we have expectation of gxn go to expectation of g of x, because this is the equivalent to convergence in law. We want to show that. Okay, so we know that by this definition, the G is bounded and measurable. Okay, so G is bounded and measurable. So this is one condition of D, but we're not done yet. What's left is that we want to show the probability that X is in CG is 1. We need this. If we can show this, then D would hold, right? When D holds, then A hold. That's what we need. Because we need this and this to say expectation of GXN converges to expectation of GX. And that's the definition of A. That's it. So then how do we show this? Here, the X is a random variable. It can take multiple possible values. And G is defined as this indicator function. And we know it has one discontinuity point. That is what? X, right? X is its discontinuity point. Before X, it takes value 1. After X, it takes value 0. So basically, we want to show what? This is equivalent to show the probability that this thing is not in a discontinuity set of G, has probability 0. So where CG is the complement. So we can say that CG is the complement of CG. So CG is the continuity set. So C bar G is the discontinuity set. Let me see. I think it looks a little vague. See if we can redo the focus. Okay. Yeah, better. Okay. So that's what I want to show. And we know here the discontinuity set of C bar G is just X, right? So we know here C bar G is just X. So then it becomes equivalent to show the probability that X equals X is probability 0, is 0. So that's all we want. But you see, we're already there. Did you see the point? If you recall the definition of the convergence in law, we also exclude discontinuity points, right? That's the definition. We don't care the discontinuity points. That's here. Let me just put it back. Here, I'm saying I only care about all X in the continuity set of Fx, and I don't care about any other points. Okay, so basically, so what I want to say is, so by the definition of convergence in law, we only care about X such that we only care about these X. So which means that Fx is continuous at X. So I think this is a good refreshment of your understanding of continuous distribution. So basically, whenever the CDF is continuous at X, it means that the random variable X will take the value X with 0 probability. Otherwise, this is if there's a point mass, then it is a discontinuity point of CDF, right? When CDF is continuous, then there's no point mass. So these two statements are equivalent. Then we're done.
Professor,
So
I have a silly question. So when we go from the probability of X has to be in the continuous set equals 1, why is it that X not being in the complement of that set equals, should it be X is in the complement of the set, or I think I just don't understand.
So are you talking about these two lines?
Yeah.
So these two lines are equivalent because these two sets are equivalent. These two sets are complement. So if random variables in one set with probability 1, it must be in the complement with probability 0.
Oh, so that's not in then when you cross through the.
Oh, my bad. Yeah, sorry, that's a typo. Yeah, yes, sorry.
Okay.
Yeah,
Thanks.
yeah, you're right. Yeah. Sorry. Yeah, I meant to say it's not in C, but I should say it's in complement. Yeah, sorry, I messed up.
Got it.
Here.
Thanks.
Yeah. Okay. So, yeah, so we're done. So from D to A, we're done. We just showed, okay, the idea from D to A is just to show this special case of G is one function in D. So D captures this. So that's why D goes to A. D implies A. And so that's why I said that we introduced the statement D for technical reason. It's for proving A. Okay. And from A to B. B is also an intermediate statement. It's so we can easily go from B to C. So from A to B, we are going to utilize that compact set. That will make things easier for us. Okay, so let's see how we're going to do it. Yes.
In that previous proof, just conceptually, is our idea that there's a function G like this for every value X in the domain of X?
In the continuity set, exactly. Yeah. Okay, so basically, let me clarify. So the proof here, which what we just look at, it's for every X. So we want to show this for every X in the continuity set of fx. So I should add this. We want to show this for any X that's in the continuity set of fx. That's the definition of CDF. So as long as we can show that for any X, we're done. So I'm trying to make the notation simple, but if it can help you understand, probably you can do this. That is, you can consider to add a subscript lowercase x here. So that will mean, okay, my G function changes with this x. For every lowercase x, I have a G function. Okay. So from, yeah.
I was not sure where did we use the measurable property in the last, like why do we need the measurable property?
Sorry, I don't understand the question.
Like we also
Can you speak
needed,
more slowly?
we also use the measurable property, right, in D?
D?
Yeah, when we say D implies A, D also has G should be measurable, right?
Sorry, I still don't understand. So are you talking about statement D?
Yes, yes.
So yeah, what's the question?
Like why do we have measurable in D? Because we never used it. So that is the confusion.
So are you saying why do we need measurable in D?
Yes, yes, yes.
Oh, I think the reason is that if it's not measurable, it will be a lot more complicated. And the reason we don't want to drop the measurable conditions because ultimately we want to prove A. And A is a function bounded between 0 and 1. And we don't, yeah, it only has one discontinuity point in A. That is this. So there's no reason we want to drop the measurable thing, right? There's no reason to go even more broader.
Okay.
Yeah. Yeah, I don't think in the whole probability theory, I don't think we actually never touch any unmeasurable function, to be honest. Because, probability theory is just a special case of measure theory. And basically, we restrict the measure to be special, the probability measure. I think that's it.
Okay.
Okay. So, okay, from A to B. So the compact set will give us a lot of convenience. So basically, I can give you the the idea behind it, but the detail is actually in the notes. So you can, if you're interested, you can read the notes in very, very careful detail. So here, what we want to do is this. So let me give you the idea. So let's say that this is the compact set, okay? So this is the compact set of G. And G is only taking non-zero value here. And outside of this set, G is 0. So let me call this X. And this is G of X. So no matter, you see, no matter how my G varies, what I can do, this is a very useful technique in analysis, is that you can always divide this compact set into small intervals. So the idea is that we're going to divide it into small intervals. Okay, and then what we'll do is that we will just use a step function to approximate this G. So what we'll do is that for every interval, we will just take the value of the center of the interval to replace the original function. So essentially, I'm going to use a step function idea. And I will call this step function as G tilde. So it's like a stepwise approximation. And why would this be useful? This can make me use the statement A. Okay, the reason is what? The reason is that for a step function, you can consider it as a summation of a bunch of the function in the CDF. So what do I mean by that? So here, essentially, you see, I can write my G tilde. Okay, I can write my G tilde as what? I can write it as something like this. So let's say I give these points on some values. Okay, so probably just to make things simpler for you to understand, I can write it as C1, C2, C3, C4. So these are the centers of the intervals, okay? Or maybe let's call it boundaries of the intervals. So here is the C1, C2, C3, C4, etc. So then you see, I can represent the step function as just something like I go from 1 to probably, let's say the last one as so the last one, I'll just give it probably Cm. Okay, I can do I from 1 to m, and I can write it as some constant times an indicator function from negative infinity to Ci x. So you see, I can make the G tilde as a sum of functions like this, okay? And I can rewrite it so you can see it more clearly. AI indicator x less or equal than Ci. So whenever x is right here, right? Then I can actually count how many Ci's are to the right of it. And then I can just count, okay, what is the weight to give to each step, and that will add up. So essentially, you see that I can write a step function using the function like this. And then you see this indicator function is what I have from my statement A. Because in statement A, that CDF function is essentially this, right? So this can be written as what? So basically, you see that and f x n ci is essentially the expectation of indicator that xn less or equal than ci. Right? That's it. So you see the connection between these two things. And because we have fxnci converges to fxci, if ci from A, we have fxnci goes to fxci if ci is in the discontinuity set of fx. So as long as the boundaries, the ci's are continuous points, are continuity points of the fx, as long as we have that, then we can have everything here converges. So essentially, you see, if ci's are picked as continuity points, then you see a natural result I would have is expectation of g tilde xn would converge to expectation of g tilde x. That's just by statement A, I will be able to get this. And then what's left is that how close g tilde is to g, right? And here that the compact set will help me, the compact and continuous. Okay, next is to show that I need those two things. Expectation of gxm minus expectation of g tilde xm is very small, smaller than epsilon, and expectation of gx and expectation of g tilde x, they are also very close. If I can have both, I'm done. Because ultimately, I want to show expectation of gxn converges to expectation of gx. But, you know, this is related to something we called uniform convergence, uniform continuity of a function. And that will give me this nice result. Okay, so this is like a important concept from analysis, uniform continuity of a function. So basically, this is a very important statement. That is, for any epsilon greater than 0, I can find a neighborhood size such that if two values, x minus y, is in each other's neighborhood, then we would have gx minus gy less than epsilon. So the uniformity here says that the neighborhood size does not depend on epsilon. That's the key thing. No, sorry, that does not depend on x. That's the key thing. So you see, this is a uniform neighborhood size. Neighborhood size. And this is in contrast to what? To continuity. You see, continuity is a much looser concept. Continuity. So continuity says that for any epsilon greater than 0 and given x, there exists a delta x greater than 0, such that for any y in the neighborhood of x, we would have gy minus gx delta. This is the continuity. So in other words, you can change your neighborhood size depending on your x, the center where it is. But uniform continuity gives you a uniform delta, no matter where x is. So you can see that uniform continuity is more continuous than just point-wise continuity. So this is stronger, this is weaker. And what's nice about this, about the compact set, the continuous function vanishes outside of a compact set, is that it implies uniform continuity. Okay, so for G continuous and with a compact support, these two things actually guarantees that G is uniformly continuous. And therefore, you see, this theory give me a foundation to construct that stepwise approximation, step function approximation. Because what I can do is that, let's go back here. So you can see that what I need is that I can decide, okay, given the approximation accuracy I need, how much do I need G tilde to be close to G? Given that, I can always find the neighborhood size so that within every interval, their accuracy is the small amount I desire. So this will give me the foundation to divide the interval into the compact set into small intervals, so that in each interval, the difference between G tilde and G is small enough. So that's why aggregating them together, the G tilde is very, very close to G. That gives me this. Does that make sense? So you can see a counterexample for uniform continuity is that if I don't have the compact support, then let's say, okay, if my function is continuous, let's say exponential function. But exponential function, you can actually grow up to infinity, right? So it can blow up. And therefore, even though you can still find, okay, given the epsilon, you can still find the neighborhood size so that in the neighborhood, the values are very close. But you can imagine, as my x goes large, the neighborhood size must go small. Because once your x is very large, a very small perturbation around it will change the exponential value a lot. So that's a case of continuity, but not uniform continuity. So uniform continuity just gives you the chance to divide the compact set into small intervals. And in each small interval and with equal sizes, and each small interval, you can have the same amount of deviation from G to G tilde. That's the foundation. That's the basic idea behind the proof from A to B. So I think I'll just stop here and I'll leave the technical details for you to read. But the key idea is to use a step function to approximate a continuous function with a compact support. That's it. Okay, and from B to C is another very interesting technique. So I want to briefly introduce that. So from B to C, you see B is continuous and compact support. C is just bounded and continuous. So there's no compact support. Then how do we do it? And here, the technique we are going to use is to multiply. Okay, so here in C, let's say in B, G is continuous and compact, right? Compact support. And in C, we just have G is continuous and bounded. So how do we go from B to C? Here, our idea is to modify C so it becomes like B. So the idea is similar from A to B. So from A to B, we modify the function G so it becomes a step function. And we can use A to prove that to prove step function. Here, C is no longer having a compact support, but we may modify C to let it have a compact support. That's the idea. So here the idea is to introduce H, okay, as a continuous and compact support function. Okay, so, and how do we do it? So basically, what we want is that this is how our H looks like. We want to find an interval large enough. So let's say that here, negative B, positive B. So how do we find this B? It's depending on the limit. So basically, we want this B is found such that we want the probability that my limit random variable is between negative B and positive B with a large probability. That's what we want. Okay, it's large. So basically, we hope this interval covers almost all the values my limit can take. And then I introduce the H function as this. So the H function takes value 1 inside this interval. Okay, that's my construction. It takes value 1. And then I let it decrease to 0. I let it decrease to 0 from this is B plus 1. This is negative B minus 1. So you see, my construction makes H bounded, right, for sure, continuous, and also it vanishes outside of the interval from negative B minus 1 to B plus 1. It has a compact support. And so with this, you see, I can now, what I do is that I just multiply G with H. I use this as my new function. So you see, this G times HX is an approximation of GX. So the approximation means that in this interval from negative B to B, it's exactly the same. And from in this small interval, negative B minus 1 to negative B and B to B plus 1, in those two small intervals, it's actually it's an approximation. And after that, this becomes 0. This may not be 0. But my construction is guaranteed that I retain the approximation to be accurate for most of the values my X can take, the limit can take. And the limit is what I care most about, right? So that's why, you see, this approximation can give me a good enough estimation in terms of expectation, because ultimately I'm taking expectation, and that's about the values inside this big interval from negative B to positive B. That's the idea. Okay, so then you see our statement B will apply to this. So based on B, I can say, I'm just going to write here briefly. So based on B, I have expectation of GHXM converge to expectation of GHX. That's guaranteed by my B. And because this is an approximation of G, that will ultimately give me C. That's it. So I can prove it for continuous and bounded. So this is something I want to emphasize as a very important technique analysis. That is, if you want to prove something for bounded and continuous function, you use step function as an approximation. sorry, my bad. If you want to prove something for continuous on the compact set, sorry, you use step function as approximation. That's from A to B. And from B to C, if you want to prove for bounded and continuous, you use bounded and compact set. You use continuous and compact set, that is the B, as an approximation to go here. That's what we do here. And finally, from C to D. Okay, finally from C to D.
Professor?
Yeah.
I'm a little confused. What G composed with H, where H of X sub n is either 1 or 0?
Oh, so this is not composite. I didn't write it in the rigorous way. It's just multiplication.
Oh, multiplication. Okay.
Yeah, just multiplication. Yeah. Yeah. So yeah, I think yeah, it's just multiplication. So it's actually, let me just write a clarification here. So this means that this is equal to Gx times Hx. This is what I mean. It's not a composite. Okay, so that's from B to C. And lastly, from C to D. This is what is also very widely used. That is, for every measurable and bounded function. So for G, measurable and bounded. So you can find an F and H that is continuous and bounded, such that you put G in the middle. You can do this, okay? And you can make this you can make their difference very small. That's it. So essentially, we're going to use approximation for the last proof again. So we want to find two functions that satisfy G, and they have G that satisfy C, and F and H have G in the middle, and their expectation difference is super small. We're done. So that's just the last step we need. And so that can generalize the statement from continuous and bounded to measurable and bounded, but with X in the continuity set with probability 1. So yeah, so that's it. I should add this. It's bounded, and don't forget this. CG with probability 1. This is very important. Yeah, so I'm not going to talk about this at all. So you can check the notes, but that's the basic idea. So from A to B, B to C, C to D, we are doing approximation step by step. And finally, we can go from D to A. So that follows. Okay, the reason we want to spend time talking about this, the Helly-Bray, right, 4 statements, seems complicated. It's because we want to give the important result, the continuity theorem. And this is called Levy, L-E-V-Y's continuity theorem. So this is the thing we will actually use to prove convergence in law. Actually, this is something we could use. It's about the equivalence between convergence in law and the convergence in characteristic function. So this is our notation for characteristic function. Okay. So I think in some of you may have learned this, another relationship called the convergence of moment generating function. And moment generating function and characteristic function are 2 ways to describe a distribution. So now actually we have seen a distribution can be described by CDF, right? Fx and Fx. It can also be described by characteristic function. And as moment generating function, characteristic function actually carries a lot of information with it. So it's a very succinct summary of the distribution. And it's a useful tool. So how do we use it, right? So basically, let's first give you what's the definition of a characteristic function. So the characteristic function, let's first define it. Definition, characteristic function. Let's first give you the definition for one-dimensional random variable. Okay, so in that case, you see this phi xt is defined as the expectation of this form, exponential to the imaginary unit I, t, x. The expectation is taken over x. T is a constant, and I is the imaginary unit. That's it. And if we have d greater than 1, okay? For d greater than 1, greater or equal than 1, the more general case, we need to have t as a vector. So t is actually rd. And this becomes an inner product, t transpose x. So if we write it out, and if x is d-dimensional, right, we can write it as expectation I, t1x1 plus 2 tdxd. That's the definition. But still, even if x is a random vector, t is a constant vector, the characteristic function is still a scalar. So you see, it's always a scalar because the inner product gives you a scalar. And one more thing that is very important about this is because I think some of you might know the Euler's formula. So by Euler's formula, we know the characteristic function is bounded because this is equal to cosine plus I times sine. That's it. So therefore, the mode of this is always less or equal than 1. So yeah, so you see the characteristic function here. So without taking expectation, this is actually continuous and bounded in t because it's a function of t. So yeah, so that's why you see statement C actually carries over, right? And we can actually immediately have, so you see, by Helly-Bray, we can immediately have, sorry, the left-hand side can go to the right-hand side. This immediately follows, follow Halibre. A to C, we're done. From C to A, it's much trickier. The reason is that if we recall what Halibre says for C, you see, Halibre C says that it needs to hold for all continuous and bounded function. So the all is the important thing, but here it's just one characteristic function. How can the characteristic function imply that it holds for all function that is continuous and bounded? That's the tricky thing. But for this one, I think I'm going to skip it and let you actually figure this out. The very interesting part for that is because of the definition of characteristic function. Its form actually allows us to do it. So a special case, so basically you can say that this interesting thing is that we can have this implied statement C in Halibre. That's amazing thing. The reason we can actually do this is because of the definition of the characteristic function. And also, we're going to utilize this by adding a small Gaussian random variable. So basically, what we want to do is that in the Helly-Bray, we want to have this expectation of xn, gxn goes to expectation of gx. And what we're going to do is that we're going to add a small Gaussian random variable to xn and to x so that the expectation doesn't change much. But adding that Gaussian random variable allows us to rewrite expectation by integrating the Gaussian density function. Since the Gaussian density function has a special form, and that special form can actually relate us to the form of the characteristic function, exponential something. And so by that, and also we need to use the Fourier transform. So by combining those techniques together, we can actually use the characteristic function convergence to prove statement C in Halibre, and that will give us statement A. So I think this is a very fancy technique that you may want to know, but it's not a requirement again. So here, the key message is that the characteristic function implies convergence in law and vice versa. So this is the most important technique, continuity theorem, for us to show convergence in law. So we'll stop here for today. And next time, so we will continue to talk about the convergence in law. So I think we are going to quickly move on to the central limit theorem. So that's the most important result. But to prove that, we need this continuity theorem because we use the characteristic function convergence to give us the convergence in law. Okay, so that's all for today. And if you have any questions, you can come to my next office hour or email me. So I hope that this is, yeah, I think we have to chat. Oh, okay. Yeah, I think problem is solved. All right, sorry, yeah. So in the future, if you have a question, you should just unmute yourself because if you use the chat, I may not be able to see it immediately. Okay, so that's all for today. So yeah, have a good day. Bye.
Thank you, Professor.
Bye. Thank you.